Hi everyone, this course, Antenna Theory and Propagation, covers two main areas, which are antenna theory and propagation. In general, the performance of an antenna is described based on the following parameters, classified based on its frequency and radiation properties. Throughout the course, there will be activities which include antenna measurement, with RF measuring equipments such as network analyzers and spectrum analyzers, antenna modeling and simulation using a full-wave electromagnetic solver, and tutorials. In this particular topic, we will go through the performance parameter associated with antenna theory and design. These include S parameter, bandwidth, impedance matching, VSWR, gain, directivity, efficiency, and polarization. Located at the front end of a wireless communication device, antenna performance parameters are divided into three categories: the circuit quantities, physical quantities of the antenna system, and the space quantities. Circuit quantities include antenna impedance, radiation resistance, and antenna temperature, while space quantities describe the properties of antenna radiation, which are field pattern, polarization, power pattern, beam area, directivity, effective aperture, and radar cross-section. Antenna design is about the skill of manipulating the circuit distribution on a conductor in order to generate the desired radiation. The properties of conductor include its size and weight. As a start, let's review on how radiation happens. When electric charges undergo acceleration and deceleration, electromagnetic radiation will be produced. Hence, it is the motion of the charges, that is currents, that produces radiation. Charges moving in a uniform velocity only radiate when the conductor or wire is either bent, discontinued, or truncated. However, if the charges is oscillating in a timely motion, it radiates even if the wire is straight. A moving magnetic field creates an electric field, while moving electric field creates magnetic field. In general, radiation pattern of an antenna can be classified either as isotropic, omnidirectional, or directional. Descriptions of this pattern include the beam width of the lobes and its 3 decibel drop, typically termed as half-power beam width, direction of the main lobes, and the level of the side lobes. An antenna exhibits identical impedance during transmission or reception, same directional pattern during transmission or reception, same effective height while transmitting or receiving. This scenario is termed as radiation reciprocity. Next is to understand the spherical geometry system. This is essential as the properties of antenna radiation pattern is quantified using this system. Spherical geometry is geometry of two-dimensional surface on a sphere. In spherical geometry, angles are defined between great circles, resulting in spherical trigonometry that differs from ordinary trigonometry. For example, the difference between the angle theta in the unit of radian and the solid angle represented by steradian is as shown in figure here. In spherical format, three-dimensional axis system is used. Angle from zenith is known as theta, typically termed as elevation, while angle from x-axis is known as phi, typically termed as azimuth. Say r is the radius. Referring this to the z angle, to the z-axis, the distance here is r sine theta. Hence, in terms of x-axis, it is equivalent to r sine theta cos phi. So the area of interest here, the blue segment, is calculated by multiplying r sine theta cos phi and r sine theta, resulting into r square sine theta d phi d theta. The solid angle or beam area in steradian is calculated by sine theta d theta d phi. The behavior of an antenna radiation is influenced by its field region, which are generally classified into three regions: reactive near field region, radiating near field region, and far field region. For near field region, this is a non-radiating region. The radiation here is highly dependent on the distance and directions from the antenna. Whereas, for the near field region, the antenna starts to radiate as electric and magnetic fields are in phase to each other. However, the angular field distribution is very much dependent on the distance and directions from the antenna. This region is estimated between R1 and R2. And finally, the far field region. This is where the antenna starts to radiate steadily. This region is beyond R2. Here, the electric and magnetic fields radiate and are in phase. They are perpendicular to each other and perpendicular also to the radiation, to the direction of the propagation. Another parameter that is crucial in defining the performance of an antenna is polarization. Polarization describes the orientation of wave oscillation. There are three situations: linear polarization, which can come in vertical or horizontal; circular polarization, which can come in right-hand or left-hand circular polarity; and elliptical polarization, which can also come in terms of right-hand and left-hand. The figure of merit that is associated to describe the polarization properties is known as axial ratio. Axial ratio is the ratio of orthogonal components of an E field. If it is linear polarity, the ratio is either 0 or infinity. If the ratio is 1, it is symmetry, hence it is circularly polarized. The acceptance definition for circular polarized axial ratio is between 0 decibel to 3 decibel. Polarization is an important merit in wireless communication system, as maximum power transmission will only happen when both polarization of the transmitter and receiver are properly aligned. Failing to do so will result in poor transmission quality. To eliminate or minimize this effect, some transmission systems prefer antenna system with circular polarization. Antenna gain is another one of the most important parameters that explains the performance of an antenna. Gain is defined as the maximum intensity radiated by an antenna to the intensity radiated by an isotropic antenna. For an isotropic antenna, the directivity is 1, hence the gain is equal to 0 decibel. An illustration to describe gain is as shown in this figure. The ideal isotropic radiator, the quarter wave dipole, and a practical antenna. Note that the notation used here is dBd with the reference to a dipole gain, and dBi with the reference to isotropic radiator. Radiation resistance is defined as the equivalent resistance that dissipates the same amount power as it is radiated by the antenna. Another parameter that always interests antenna designers are the directivity. Directivity explains the ability of antenna to focus its radiation energy in one or more direction. D theta phi is the ratio of radiation intensity of an antenna to the isotropic source radiation intensity. It is described in the unit of watt per steradian. Radiation intensity describes the power radiated from an antenna per unit solid angle. Radiation efficiency is the ratio of power radiated to the input power. Effective area of an antenna is the equivalent area where incident power is equal to the received power. Mathematically, it can be described as effective aperture, as shown here. As for the circuit quantities, the parameter associated to the performance is the performance of an antenna is its operational bandwidth. Bandwidth are influenced by the antenna impedance. Bandwidth is described using the following terminology: return loss, VSWR, and Smith chart. Let's have a look on a system that is illustrated here. Say the incoming signal or the incoming voltage is labeled as V positive, and the outgoing is labeled as V negative. The power reflected by this antenna system is tau square, and the power entering the antenna system is termed as 1 minus tau square. The first representation is the return loss. Return loss is also known as the reflection coefficient. It is the ratio of the reflected voltage to the transmitted voltage. The cutoff acceptance value is negative 10 dB. Let's have a look on this example. The reflection coefficient graph of a dipole antenna simulated earlier. The bandwidth is calculated by subtracting the lower frequency bound at the 10 decibel cutoff from the upper frequency bound. In this case, the bandwidth is 412 MHz, which is approximately around 17%. F0 here is known as center frequency. The second representation is known as voltage standing wave ratio, VSWR. VSWR is a way to measure transmission line imperfections, which is generally caused by impedance mismatch. In this case, between the output port and the antenna connected to it. This figure illustrates the standing wave phenomena. As seen here, reflection reduces the value of original signal, resulting in the standing wave. The acceptance cutoff value for VSWR is 2. the return loss correlates with VSWR. Hence, as shown here for the same dipole simulation, the bandwidth is 412 MHz, similar to the one shown in the reflection coefficient graph earlier. The final representation is Smith chart. A Smith chart is basically a graphical way of viewing the input impedance. The center of the Smith chart represents zero reflection coefficient, so that the antenna is perfectly matched. While the perimeter of the Smith chart represents a reflection coefficient with a magnitude of 1, which means all power are reflected, which indicates that the antenna system is very poorly matched. The reference bandwidth cutoff value in this Smith chart is 0.316. The value carries the information of resistance and reactance of an antenna. Positive reactance indicates inductive circuit, while negative reactance indicate capacitive circuit. The Friis transformation equation is used to calculate the power received from one antenna when transmitted from another antenna, separated by the distance r and operating at a frequency lambda, wavelength of frequency. This formula can be represented in watt and decibel. So we had gone through a couple of parameters that is describing the performance of an antenna system. These parameters will be used when designing and analyzing the performance of antenna throughout this course. In the coming chapters, we will look into 4 clusters of antenna design: electronically small antenna, resonant antenna, broadband antenna, and aperture antenna. Electrically small antenna has structure which is much less than the wavelength. Resonance antenna operates well at a single or selected narrow frequency band. For broadband antennas, the pattern, gain, and impedance remain acceptable and are nearly constant over a wide range of frequency. While for aperture antenna, they have a physical aperture through which the wave flow.